Okay, perfect. So we are now on day 4. And it may be the case that we actually see math today. So, so far we've just mostly had a conceptual interaction with calculus, which is good. So before we go in, let's see. I have not yet edited those Anki cards that the reverse is used incorrectly. But I will do that here soon. I think the only... Oh, okay. So I recall what we were looking at before we ended last time. Okay. Could you tell me about indefinite integrals and how the indefinite integral of a function is the set of all antiderivatives for that function? Okay, so this question was about, if you'll recall, we had integrals and derivatives. Indefinite integrals, or there were two types of integrals. There was indefinite integrals and definite integrals. A definite integral is, and this is for an integral being, we're looking at like the volume under the curve. And a definite integral has a distinct stop and start. And then an indefinite integral returns this like a set of the family of functions that and that's where my kind of understanding stops. I'm not sure what that's all about. So the first thing I'm thinking of, so I know it's a set of functions, and I know that C represents a constant, and if we take a derivative of a constant, it's always the... Oh, okay, yeah, that's correct. Okay, so I was thinking, maybe it's the case that the set of functions, the set of antiderivatives, are really this, like, pretty much the same function, because the constant turns to 0. So it's a set of functions because of the variation within the C value or constant. And so I would have f of x plus 1 plus 2, f of x plus 3. So pretty much f of x plus n, where n can be any number or any constant, really. Okay, so I feel good about that now. Okay. Okay. So I want to sort of understand a little bit more about the relationship between indefinite and definite integrals. So I know that for a definite integral, I'm returning a value. And what I'm wondering is the function of an indefinite integral useful for turning it into a definite integral? Like is an indefinite integral, like, is it possible for me to then go and return a numerical value from like using the indefinite or the antiderivative as integrated from as an indefinite integral? Okay. And then additionally, I think I need one about I'm going to browse. Let's see. Okay. Okay. Oh. I think this is less than I am. Let's see. Okay, let's look at calculus. Okay. No. No, I'm wanting math. Okay. So I am doing... I need to do a better job at getting these to the right one. Looks like I didn't have all of them in the right place. Okay, so let's see. So those are in calculus now. Okay. Okay, perfect. Sweet. Okay. Now we're going to go back to the calculus deck. I'm going to browse. Okay, so I think I do need some more cards on integral derivative. Okay. I swear I had a card that was like on the fundamental limit or the fundamental theorem of calculus. So I am unsure if I am actually... so we'll go back to the default and then... Okay, lambda calculus. Okay. I think I have some more cards that need to be in the calculus deck. Okay, and so typically I wouldn't have to like look back over my cards that I've created to figure out which ones I need to create more. Typically I sort of go in a stepwise fashion, but because this is broken up into 1 hour chunks, my ending point isn't always like clean where it would be if I was going through this alone. Okay, so that is all there. And now let's go back to calculus. Perfect. Okay, so... Okay. Okay, perfect. I think we're ready to head back to that. Okay, next card will be how derivatives and integrals relate. And then I'm then going to go okay, actually I do need that syntax for f prime to be there. Resulting derivative. So what's the syntax for resulting derivative of f of x? And hopefully that gives me the right... oh, sweet. Perfect. That's what I was looking for. And the nice thing about large language models is it helps validate, like, I had a particular answer in mind for this derivative here, and then I was able to get it. So that is good. And I think I did not add tags. Okay. Perfect. Okay, so we'll add that in here. And then I think I'm going to wait on these additional definitions. Oh, actually, I do want to investigate the indefinite integral. Could you tell me more about indefinite integrals? I understand that it returns the set or family of functions called antiderivatives that integrate to it from the source function, period. Oops. Can I then, after having taken the antiderivative, using an indefinite integral, use that function to then generate a definite integral? Or I guess what I'm saying is, after I take the indefinite integral, can I use that to pull out a numerical value, like total volume under the curve? Or if not, what is the use case for indefinite integrals? Oh, wait a second. So a definite integral is merely the resulting indefinite integral minus, at one point, minus another indefinite integral. Is that correct? Ensure that this is correct. Be careful around the constant, because that could be an issue, because in the definite integral that's not specified. So would then a definite integral return the total volume under the curve? Oh, shoot. Okay, so I'm wondering now. So it seems like a definite integral is merely two indefinite integrals. I feel like this is wrong, though, a little bit. Anyway, so I'm just trying to get a conceptual understanding, so I'm hammering this out. It may be that like I update dramatically for what these things are. But let's tease it out. Okay. I have a few questions. One, how would I get the total area under the curve? Could I do this with an indefinite integral, or would I certainly need a definite integral, period? Also, I'm wondering how indefinite integrals and definite integrals relate, period. When I'm working with a definite integral, is the definite integral merely taking two indefinite integrals or antiderivatives and subtracting them? Okay. I see. Okay, so it is the case that it's essentially the difference. So it's essentially the difference. Is it exactly the difference, question mark? Okay. Okay. Is it improper to call an antiderivative an integral? Oh, I see. Okay, so there are a couple things I want to capture here. So, so with this difference between indefinite and definite integrals and antiderivatives. So an antiderivative is an instance of an instance of an indefinite integral. Oh no. It is a member of the set. Let's see. So when you take an indefinite integral, you get the set of all functions, or the family of functions, who vary along the constant. And so when we're talking about indefinite integrals, it's not quite the same as an antiderivative, even though sometimes they're used interchangeably, because indefinite integrals are describing the family of functions rather than just the result of taking an integral for a function. Okay, I feel good about that. Okay, perfect. Can you now formulate that into an Anki card as well? Okay. I do want to see if I have an antiderivative card. Okay. Okay, I think we're feeling pretty good. Okay, so now I'm uncifying the question about whether or not it's proper. It's not exactly. I wanna. Okay. Okay. I'm feeling pretty good about that. Okay, now this question here has me wondering that I've just totally got something wrong here. Well, so we have the constant of integration where we add c when finding the indefinite integral. And so maybe the indefinite integral is that family of functions. But if we ever use the definite integral, I think we just drop the constant because we'll just see. I'm pretty sure we just drop the constant when we're using it in a definite way, or we're using the antiderivative or the definite integral. Let us see. Okay. That's not what I was wanting. Oh, okay. Um, I see. Okay. Um, Okay. So I was think I was a little bit hasty in with the constant portion. Um, so okay. So the issue I had just there was that I think I was just mixing up differentiation and integration a bit, because for differentiation, it eliminates any constant, um, but for integration, it's not the case. Okay. Um, okay, this will be a good card. So this is sort of meshing those two ideas together about the behavior on constants in differentiation versus integration. Integration. Okay. Oh, okay. No, that's good. Oh, okay. So the process does. Oh, interesting. Okay, so the process does. It does cause. Okay. So I'm going to put this in here. This is something that I will understand more once I do it once. Okay. Okay. I think this is probably also a good question to have. So to really lock in the idea. I forgot. This in Obsidian, the Vim implementation does not allow you to pull into the copy buffer of the system. Okay. Oh, okay. I think when I was getting mixed up, it's because antiderivative and derivative. Um, I was thinking of derivative when it should have been antiderivative. I do add, like in calculus or in regards to, for some of my Anki questions, because I have varying topics, I like to give just a little bit of more context. Sometimes that's helpful. Okay. Okay. I think I am... Oops. Okay, so this one's understandable. This one makes sense. Okay, I think this will also be important. Perfect. Okay, so now I'm wanting to honestly just grab the question because I want to make sure that I have the right stuff here. Okay, perfect. That's what I was thinking. Okay, so now we have that. This is actually also a good question. So this question, why is an antiderivative of a function called an antiderivative and not an integral? And the reason being is because of the nature of the indefinite integral and how we are not returning, but it represents the family of all functions the family of all antiderivatives who emerge, or let's see, the family of all antiderivatives. The family of all antiderivatives of f of x. Okay. That's right. That's a good way to put it. Copy. Okay. You know, I'm surprised that I am... I guess it makes sense because I haven't... So it's in response to why is an antiderivative of a function called an antiderivative, not an integral. It sort of beats around the bush. It does describe it, but only like tangentially. I'd like to have it give like a little bit more context here because for someone not like that doesn't know calculus, yielding this family, which is talking about the like indefinite integral. Oh, actually, well, I think I will grab that. I do like that. Oh shoot! I have not been sharing my screen. That's a shit moment. Oops. Okay. Perfect. So I've just been going through. Okay, so we'll continue. Okay, so okay, so I guess I'll kind of give like a recap of what the last few have been. I had some questions here that were from the previous day, and they were kind of to prime me for being ready to like start up. And so I mostly made Anki cards of those questions. These are questions like regarding like this, how do I represent an indefinite integral? What happens to constants in integration? More about how definite and indefinite integrals differ, and how they relate to antiderivatives. Yes. And then I've just been adding Anki cards to this. Okay, so now that we've... I think we can come back here. Could you give a brief introduction to the limit laws in calculus? I do have one more. Let's see, we'll zoom in here so it's easier to see. Limit laws were another thing that was on my list of things to be able to bootstrap myself in. Okay. Okay, so limit laws are a set of rules that simplify calculating limits by breaking down complex expressions into simpler parts. For example, constant law, the limit of a constant is the constant. Sum difference law, the limit of a sum or difference is the sum or difference of the limit. Product law, the limit of a product equals the product of the limits. Quotient, the limit of a quotient equals the quotient of the limits. Power root laws, the limits pass through exponents and roots. I see. I see. So these laws help identify the limits of functions. Is that right? Okay, so... Okay. So, as part of some process, we have to identify the limit. And the limit allows you to break down functions into simpler parts. And those simpler parts... or you can derive limits from those simpler parts using the limit laws of calculus. I think I will. Make an Anki card of that. So it gave me a sort of ostensive definition for what the limit laws are. I'm looking for more of like a practical definition of like what like use are the limit laws within calculus. And so actually I should just rephrase my question. The use or the use of limit laws it's often the case. This is a thing similar in programming where it's like the program is never wrong. Of course, like asterisk, but it's like the person who coded it wrong, right? It's going to logically flow from it. And so this is another instance where it's like I asked the question and I was wanting something particular, but I didn't get the particular thing because I didn't ask it. Okay. Okay, I like that. I think so. I did talk about earlier how you should avoid doing multiple parts. It's only 5 here, and these will be pretty easy to retrieve. And I think I'm only going to want not the content of the law, but the name of the law. And the reason why they're going to be easy to retrieve is because we pretty much just have like the operations you can do in, basic mathematics, like quotient, product, sum / difference, power / root, and then you have a constant. So these will be pretty easy to retrieve. And so I'll specify, I'll just say 5 names. Okay, and then what is the constant limit law? What is the constant limit law? Okay, we'll see if this is the right way of asking it. I think it is, but I'm unsure. The constant limit law. Okay, perfect. I'm not sure if it's like the constant law, limit law. Looks like constant limit law is fine. Okay. Okay. So could you rephrase your answers to be the answer of a question of this format? What is the And I'm thinking now, so I don't super like how concise these are. So I'd like something that is a little more verbose. And I think I'm going to be making like a system message, because there is like a preset thing. Because I'm finding that I'm having to tune my Anki cards quite a bit, and I didn't really think about this like in when I've created these in the past, right? But yeah, I think that might be beneficial. Okay, perfect. This is what I'm interested in here. Okay, perfect. Okay. Okay, so now I'm asking for like an English description, and then the formula for that, because that's the better approach when it comes to these. And I'm just noticing that these power and root laws were actually. Yeah, they were put under the same umbrella here. And so I might have to adjust that. Okay. Okay. Okay, so now that we've done those things, I kind of want to go back to the initial one. I think I'm going to yank out this thing we initially generated as sort of a roadmap for this like portion, or for our like document here. And I'm still kind of figuring out what I'd like this document to be. Right now it's sort of being just my scratch pad, but yeah, we'll see how this develops. Okay, so now that we've like spent just 3 hours, or let's see, we're on hour 4 now, maybe hour 3 and some change, like just learning about calculus. I know what the concept of limits are. I don't have the techniques yet, and I'm not 100% sure like what is meant by continuity and discontinuities. So I actually might just grab that so we can learn a little bit about that. Because if I understand these terms, even before I go into this video more, I'm just going to be way more well prepared to be able to fit these terms in their sort of atomic, in their like current atomic state within the broader the broader context of calculus. And so I'm not worried at all about how much time we're spending here. Okay, so we'll just go back to the top now. Okay, so I'm not 100% sure what we have for continuity here. And I think actually by computing limits, they may just be talking about the limit laws. So I actually may know, obviously I have zero practice with that, but okay, so I know different derivatives and basic differentiation. Obviously I can't do it yet, but I know what they are in terms of inputs and outputs and conceptually. And then I also understand integration and the fundamental theorem of calculus. The fundamental theorem of calculus connecting or being the sort of bridge between integration and differentiation, and how integration and differentiation are sort of inverse functions. And then, okay, yep. So I understand what antiderivatives are, what definite integrals are. Okay. So now I need some problem solving skills and algebraic manipulation, which is not bad. I think I could do that. And then I do need some notational fluency. We did grab some with the integral sign, the big S, and then also the d over d of x for differentiation. So that's pretty good. Okay, so I guess we're getting the logical foundations now. I probably don't have like the mathematically precise definitions, though I feel like I'm reasonably close. Obviously a bit better to have like, boiled down as much as we have or as much as we can, right? But I feel like we're doing good there. For uniform continuity, I have no clue what this guy is. So we'll just put him at the bottom. So continuity is something that I need to understand. Oops. Okay, so jump. Okay. Okay. In-depth differentiation, proofs of rules. Okay, so obviously have not interacted with the proofs at all, or higher order derivatives. I'd like to grab that. And then haven't done any theorems. Okay. I think the Riemann integral maybe would be good to know as well. So we'll also grab that. I think probably power series and Taylor series are also something that'll be important. Okay. Okay, so we'll put these down here as sort of like a roadmap for what I need to think about next, maybe. I think we will go over continuity. What could actually, we are at 11:15, and so we have still made it 4 hours now into learning calculus without doing calculus, and so I'm feeling pretty good about that. Or finishing this video. So we're going, I guess what has been the case is that I've enjoyed or preferred the conceptual approach first. I think partially because I haven't taken mathematics since, or I haven't done any mathematics since high school. I did take a stats class in college, but that's like the extent of my mathematics. So maybe I just prefer this like conceptual oriented one first. And so that the topic that will be more difficult probably in the like actual mathematics themselves will be like sort of propped up a bit by my strong conceptual or my better conceptual understanding. And then also because I do have a background in computer science, I think probably understanding functions generally or understanding things in terms of functions I would think comes a little bit easier to me because that's what I interact with. And so I think like my aha moment about the nature of the fundamental theorem of calculus with integrals and derivatives was, I think, as probably as a result of me like maybe having that background or being able to think about it from that perspective. Okay, so let's see. I think we'll end there. I'm feeling pretty good about that. And I think next time, fingers crossed, but I believe we will be able to start this. We will be able to start this video. So I'll see you guys probably Monday. Though I am really just enjoying going and doing an hour of calculus every night. And so I may be able to try to get something to work to have this on a daily basis. But we'll see how that goes. Like I'm really enjoying this, so like it's feeling good. Okay, now I'll see you guys tomorrow.